Alright, so when we were in class we kind of stopped halfway through these notes here and took a little break, so if you need to do that, feel free to. Alright, so first question, got initial point, terminal point, so you have a vector, so negative 2, 3, so go ahead and draw that vector, starting at negative 2, 3 and then ending at 2, 6. Right, and it's asking if that vector, W, is the same as this vector V that starts at 3, 6 and ends at negative 1, 3. So when you get those drawn, then you look at them, and they are pretty much the same. They just go the opposite directions. So the answer to this question would be no, they are not equivalent because they do not go the same direction. But they do have the same slope to them, kind of like the same angle in a way, but not really. That's what makes them different. One's going up that way, one's coming down this way, but they also do have the same length. So let's take a look at this vector V, because they both go over 1, 2, 3, 4 and up 1, 2, 3. So think of that as a right triangle, right? So they go over 4 and up 3. So that would be a 3, 4, 5 triangle, right? And the reason you know that is because you made like a right triangle. Now in this V vector here, it is going down and left, but even if this was negative and negative, when you do your Pythagorean theorem, you would still get positive 25 right here, and so C would still be the 5. Okay, so that is your length. So that is going to have to do with finding the magnitude. Maybe remember the magnitude of a vector is how long it is. So they're not equivalent, but they do have the same magnitude. Right? They are just opposite vectors because they go in the opposite directions. The reason we also know this is because if we find the component form of W, remember you do the end minus the beginning, so 2 minus negative 2 is 4, and 6 minus 3 is 3. Whereas if we did the same thing for vector V over here, oh my gosh, my pencil. Vector V, we do negative 1 minus 3, so negative 1 minus 3 is negative 4, and 3 minus 6 is negative 3. So you see they are pretty much the exact opposite of each other. All right, so that brings us to our formula here for the magnitude. So it's like the Pythagorean theorem. If you know the x component and the y component, you basically square them, add them up, do the square root. So that's our formula for the magnitude. It is the square root of the x and the y component squared added together. Okay, so go ahead and pause the video and see if you can find the component form and the magnitude of this guy right here. Alright, so if you did that, your component form here of W is negative 1 minus 4, negative 5. 5 minus negative 7 is 12. And then we did the magnitude of W, the square root of 25 plus 144, right? Because you square both of those and add them up. So square root of 169, which is 13, turns out. It doesn't turn out perfect always, but you know, this time it did. Sometimes you get left over with a radical. Alright. So you do some operations now that you know all about component form. Let's say we want to do 2W plus V. So you want to do 2 of these plus that action right there. So 2 of those. So 2 times 3 and 4 would be 6 and 8. Plus V is negative 2 and 5. So component form is very nice. You just add up the like parts. 6 and negative 2 make 4. 8 and 5 make 13. Okay, negative V, so here that would be the opposite of this, so positive 2, negative 5, and add W, which is 3, 4. And again, you just add up the parts, so you get 5 and negative 1. So you can do this instead of like drawing the picture and everything. Alright, so take a second and pause and find the answer to this guy here. Alright, so hopefully you found negative 3 times W gets negative 9 and negative 12. And then plus half of V, so that would be negative 1 and 2.5. So you add these together, you get negative 10 and negative 9.5. If you had to, you could find the magnitude now, you could draw it, whatever you needed to do. So this next one's a little bit strange, but something called a unit vector. So remember, a unit vector is 1 unit long, right? And it has to go in the same direction as its original vector. So what happens is if you have a vector, like let's say you have vector v right here, and you want a unit vector, well, that unit vector would have to go in the same direction as this one, but it only has to be 1 unit long. So basically, I want another vector that goes in the same direction, but it's shorter, right? And so what you do to find a unit vector is you take the original vector and you divide it by its own magnitude. Okay, so basically what you're going to get is you're going to get a divided by the magnitude of the vector and b divided by the magnitude of the vector. So you divide it by its own magnitude. Okay, so if I'm going to find a unit vector in the direction of b, I have to find the magnitude of b. So the magnitude of b is the square root of 36 plus 16. So let's see, 46 adds up to 52. So the square root of 52. Well, 52 is 4 times 13, so this is 2 radical 13. So what I'm going to do is I am going to have a new vector, and I am going to divide these by my magnitude. So 6 over 2 radical 13 and negative 4 over 2 radical 13. Now you can reduce this. 6 and 2 reduced to 3. And this reduces to negative 2. Now, you can also rationalize it, but we can just leave it like this. It's not that big a deal to rationalize it, but if you had to, you could. And I just want to prove to you something. Let's go ahead and do the magnitude of this thing. So the magnitude of this would be the square root of each of these parts squared. So if I square this, I get 9 over 13. And if I square this guy, I get 4 over, if you square radical 13, you get 13. So look at that. We get the square root of 13 over 13. 13 over 13 is 1, so the square root is 1. And so that's just proving to you, you don't have to do that every time, but it's just like proving to you that the magnitude is now in fact 1. So this new vector maintains the same direction as your original, but the magnitude of it is 1. All right, so then we come across what are called standard unit vectors. So when you have an xy axis, and let's say you want to go just 1 unit in the x direction, that is called a standard unit vector, 1 unit long, so you would call that the vector 1, 0. And j would be the vector going up in the y direction 1 unit, and that would be 0, 1. So what you can do here, every time you have a vector, like let's say you have a vector like 2, negative 3, right, that vector, vector v. There's another way you can write it. You can write it as 2i minus 3j, because what you can do is you say you have 2 of these, right? You have 2 going 1 in the x direction, minus 3 j's in the y direction. So basically you have 2, 0 minus 0, 3, and so you get 2 minus nothing is 2, and 0 minus 3 is negative 3, and so it's just a way, basically, like these two things are equivalent. They're basically just different formats of the same thing. So just get used to switching between component form and i's and j's and all that kind of stuff, okay? So it's just like another way to write the same thing. It's called standard form. Alright, so basically what we're saying here is that another way to write a vector such as 3, 4 in, this is component form right here, but in standard form I would write 3i plus 4j. And so what it does is it makes it easier to do like combinations of things, and so we'll talk about that in a second. So find the standard form of a vector. Here's my initial point, here's my terminal point. So I personally like to say to myself, well, let me just go ahead and do the component form, then I'll switch it. So negative 1 minus negative 2 is 1. 5 minus negative 8 is 13. So I basically have that vector b is 1i plus 13j. Okay? It's just another way to write it. Alright, so down here, so it's just, again, another way of looking at it. If somebody gives me u and v like this, I can now do 2 times u, so 2 times 4I minus 2j minus 3 times v is negative 6I plus j. And so that way it's like combining like terms. I get 8I minus 4j plus 18I minus 3j, and so my final answer, my vector is 8 plus 18, so 26I minus 7j. But that's just the same as writing 26 comma negative 7. So like these are the same thing. This is component form and standard form. Okay, so it's just a matter of preference a lot of times. All right, so when your vector is in standard form or component form, it's very easy to find the angle of that vector, the direction angle. And so let's go ahead and look down here. And if I have this vector, I have, what is it, negative 4 minus 2. Let's see, negative 4I, so I go 4 back this way and down 2. So here's my vector right there. So I basically want the angle right there. But also remember, this is in the third quadrant, so it's going to be 180 plus whatever that angle is. So let me take this and draw this off to the side. So I have this little triangle right here. I have a right triangle, so it should remind you of some trig. We have gone left 4 and down 2. So how do I find this angle? Well, hopefully you realize it's the opposite over the adjacent. So the tangent of that angle is my negative 2 over negative 4, right? The opposite over the adjacent. So that's 1/2. So to find that angle, I'm going to have to do the inverse tangent of 1/2, basically, right? So grab my calculator, make sure it's in degrees. Yep. All right, so second tangent of 0.5, I get 26.6. So 26.6 degrees. But remember, it's 180 plus that 26.6. So 180 plus 26.6. So my angle of this vector right here is going to be 206.6 degrees. Okay? So let's turn that into a formula up here that we're going to write here. So to figure out the angle, what you do, usually a vector is given to you in component form, like a comma b. You know, that's our x value. This is our x value and our y value. So what we're going to do to find that angle is we will set up this equation. Tangent of my angle is equal to b over a, and we will solve for theta like we did here. But that's my main formula there. You can also draw it out and you can kind of see it. All right, so now would be a good time to take a little break if you want. All right, so if you know the magnitude or the length of your vector and you know the direction angle of the vector, like we just figured out here, then there is an easy way to write the vector. You're basically going to take, remember from the unit circle, the x value is the cosine, the y value is a sine, and you're going to take that, basically that unit vector, and you're going to multiply it by its magnitude that you want in the problem. Okay. So for example, if I want a vector that has a length of radical 13 and makes a 60-degree angle with the x-axis, so I want 60 degrees right here. Okay, so we are going to call that vector v, I guess. It doesn't say really. I'm going to put radical 13 here. I'm going to multiply that by the cosine of 60 degrees, comma, the sine of 60 degrees. And you can put it in component form or IJ form, or standard form, doesn't matter. All right, so then we think back to myself. The cosine of 60 degrees is going to be 1/2 from the unit circle. The sine is radical 3 over 2. All right, so multiply these together. Radical 13 times 1/2, radical 13 over 2. And radical 13 times radical 3 gets me radical 39 over 2. All right, so this is that vector. Okay, so if you're told a magnitude and an angle to adhere to, that's how you do it. All right, so find the component form that represents the velocity of an airplane descending at a speed of 100 miles per hour, so there's your magnitude, at an angle 30 degrees below the horizontal. Now I'm going to draw this way. I'm going to say, 30 degrees below the horizontal. So this plane is here and it's going down, right? It's going down by 30 degrees. So it's actually like negative 30 degrees, I could say. All right, so, but somebody pointed out in class that you could very well be going this way as well. I mean, you don't really know. So I guess if I ever give you something like that, I'll give you a picture or something. But I'm going to just do it this way. So here we go. So my vector, I have my magnitude, and then I have the cosine of negative 30 degrees, and then I have the sine of negative 30 degrees. Now, I could very well use negative 30, or I could use positive 330. Either way, the coordinate right here is going to be square root 3 over 2 and negative 1/2. So because these are unit circle values, I can like get the perfect answer, but you know, you can also put them in your calculator like you'll see on the next example. So let's see, I got 100. My vector is radical 3 over 2 and negative 1/2 for my cosine and my sine. So I will get 50 radical 3, and here I'll get negative 50. And of course I could write this also as 50 radical 3i minus 50j. Like you could write it either way. Like this could be my vector as well. Okay, so it doesn't matter how you write it. It doesn't really say. Oh, it does say component form, so I guess this is the real. All right, so we are only going to do this top example here. So go ahead, and we're not going to do this example, which means I think it's number 53. Yep, 53 we're going to cross off in the homework right there. All right, so this here, three forces with different magnitudes are acting on an object at different angles respectively, and we want to know what happens, what's the result of these three things happening. So basically you have an object sitting here, all right, and something with a magnitude of 70 pounds is going to pull it this direction. So this is like my, my XY axis here, and it's going to pull me down 30 degrees, so 30 degrees, negative 30 degrees, and that is 70 pounds. Right, then it's 40 pounds pulling at 45 degrees, so 45 degrees, not as long, so that is 40 pounds, 45 degrees. And then we have something pulling with 60 pounds of force at 135. So 135 is like over here, 60 pounds. And this angle right there is 135. Okay, so basically we want to know like what's going to happen. Where is this object going to move? Now I got more things going this direction, so it's probably going to move like something like this, like up in this direction, but who knows. All right, so we need to make up vectors for each of these things. So we're adding these vectors together. I want to know the result of being pulled by these three things. So my first vector is going to be 70, and then the cosine and sine of negative 30. So 70 cosine of negative 30, and then 70 sine of negative 30. I'm going to add that to the other next vector is 40 cosine of 45 and 40 sine of 45. And then add that with the last one, so 60 cosine of 135, 60 sine of 135. All right, now since I want to add these together and I want the result, I'm trying to add these all together, I'm just going to put them right into the calculator. So you need to add the x's to get my x value and add the y's to get my y value. So I'm just going to go ahead and say to myself, let's see, 70 cosine of negative 30 plus 40 cosine of 45, and my calculator is in degrees, and 60 cosine of 135. Oh crap, I just messed it all up. Hang on. 70 cosine. Alright, so my x value is 46.5, we'll say. And what I can do, if I press second enter, it retypes that, and I just got to change all these cosines to sines. So I'm going to go back to the beginning and change them from there. So I need a sine instead, and here I need a sine. I already changed the last one. Okay, there's the second part, 35.7. Alright, so this is my resultant of those three things acting on the spot right here. So the result is it kind of goes off in this direction like we thought. And so, but I need the angle, I need the direction, the angle, and the magnitude of this thing. So I'll call this vector v. So the magnitude of this thing is going to be the square root of 46.5 squared plus 35.7 squared. So this comes out to 58.6 pounds. Okay. And I need the direction. So I need to do my tangent of my angle. I need to figure out the angle. And my b over my a, 35.7 divided by 46.5. So the angle that I get, and this is in the first quadrant, you know, right and up, so it's in the first quadrant somewhere, so I don't really have to adjust my answer. So my angle, if I put that in my calculator, comes out to 37.5. Alright, so there is the answer to the question. Alright, so you should find yourself able to do all these problems here, and I'll see you in class.